So
welcome to the latest product quality cleaning workshop webinar. We're excited to be talking about non-ionic surfactant chemistry in our formulations. These workshops are put together by the PQCW team, the product quality cleaning workshop team. And that's Barbara and Ed Kanegsberg, the cleaning lady and the rocket scientist. Here's all the information about them. They give what I like about them the most is common sense expertise and an independent view on how cleaning processes could be improved. One of the quotes of theirs that I like the most is that cleaning is a process, not a chemical. And so we'll see that from today. We have a discussion on the chemicals that go into formulations, but then how it fits into the whole process.
That's right. And
then, go ahead.
We love working with the professor. Darren actually loves to teach, and he's Dr. Darren is professor of physical chemistry at Sam Houston State University, and he's the leader of the cleaning research group, which helps students to become cleaning ladies and gentlemen of the future. Right. He is a co-chair of the product cleaning workshop, and he does he says he likes to chase squirrels. So he performs cleaning trials and compatibility, all that good stuff. And there's our contact information.
Yeah, you certainly email us with any of your questions. Now, if you'll notice in the workshop, the Zoom session down at the bottom, you have a Q&A button. And click that, those questions come straight to the panelists. And so we'll be able to see your questions. And they're also saved for us. So if we don't have time to get to your question, we'll send a follow-up email to the list and you'll get your answer directly from us. And if you think of something after you've left, you can always check our emails and contact us directly.
And if you don't like the answers, you can ask us again. We'll make another answer.
And I'd like to also put a plug in for our workshop. This is a chance for you to dig deep into the science and art of precision cleaning. Here's some comments that we got from an attendee of our most recent workshop. And so I think that specifically like the one where it talks about changing their processes right away after the workshop. So they found good practical tips that they could implement without going through huge capital improvement purchases. Some of the small things you can implement right away.
Yeah.
And so we're very happy to have Stephanie Cole join us today. She's from Clariant Corporation and she's a senior formulation chemist. So we get to actually look under the hood of the aqueous cleaning formulations and learn more about the non-ionic surfactants that she's been working with.
And a formulations chemist. What is a formulation chemist? It's a chef, basically.
Yes.
Right.
Exactly.
Yes.
And I like that she has a Bachelor of Science in Chemistry and a marketing minor, so she's seen both sides of things, and that's really valuable. So I'd like to give Stephanie control of the mouse here, and then we'll let her take off and tell us what she has to show. Go ahead. See if you can click.
Okay, I just clicked.
All right, very good.
There we go. Okay. Well, thank you, Barbara, Ed, and Darren for allowing me to present the work that I did with my colleague and I over the last couple of years on this topic of post-machining cleaning. And thank you for the audience for being here. I feel like this will be a great interactive presentation. Definitely utilize the question function on this webinar so I can help with anything. So I'm going to take you along a journey that my colleague and I, Ashley Milton, went through over the last couple of years. We learned several things during this time, and I'd like to share them with you. The main takeaway from this presentation is that I want you to challenge your surfactant manufacturer and formulator to design molecules and formulations that address your pain points. So keep this in mind as I click through this presentation. So now for our agenda for today, I'll give you a brief overview on Clariant, our production sites, our R&D facilities, and some of our business lines. Then we'll look into the metal cleaning market, the life cycle of a metal piece, solvent versus aqueous cleaning, the types of aqueous cleaners, surfactant chemistries, test methods associated with metal cleaners, and then the results. So Clariant is a global company with manufacturing sites all across the globe. We have several R&D centers, including one in Mount Holly, North Carolina, which is where I reside. We also have Clariant Innovation Center in Frankfurt, Germany, and we have several business segments, including care chemicals, catalysts, and natural resources. It's then broken down further, and the area that I work in is industrial applications under industrial lubricants. Our core knowledge is EOPO derivatives, which I'll get to in a minute. And for this presentation, I'll speak about surfactants related to this base product. So let's go back in time to 2019. So I just started my new career here at Clariant, and I was a part of evaluating the market for metal cleaners. Clariant has extensive knowledge in surfactants, but our expertise with the metal cleaner market needed a little bit of attention. So my colleague and I dove into this project and discovered a few things. There are some pain points associated with the metal fabrication process, including corrosion and maintaining a certain level of cleanliness. So even as the fabrication process changes, the metal cleaning process remains a vital piece in the fabrication process. The global market of cleaning chemicals is expected to grow 5% with $16.5 billion market value by 2025. So this was an exciting discovery, and this led us to dive further into this project. So to understand how cleaners play a role in the fabrication of a metal piece, we need to look at the life cycle of this metal piece and understand what issues might arise during the lifespan from a production to assembly. So imagine you have a sheet of metal, and the plan is to turn this metal piece into some sort of widget. The highlighted steps here show where surfactants can be used as you look across the metal life cycle. So for example, in shipping, fabrication, cleaning, surface prep, and storage are all places where surfactants can be used. And then the statement below each of these steps indicates the issues that might arise during the metal fabrication process. And so as you can see, and I'm sure most of you already know, there's lots of places where product defects can occur, causing unfortunate scrap of metal pieces. So let's quickly compare solvent cleaning versus aqueous cleaning. So typically the decision is made in the early stages of the cleaning plan on whether to choose solvent or aqueous cleaner, or you might choose both. So this presentation focuses on aqueous, but I'll briefly describe both processes real quick. So solvent cleaning has the same purpose as aqueous. The idea is to remove soil and metal chips from a surface. It's typically used at a higher dose rate, 100%, and the cost is generally higher. It's very effective at cleaning and can be used as a pre-cleaning or even a post-cleaning step. So the common solvents are shown, which is mineral spirits, halogenated solvents, and alcohols can be used for this. Aqueous cleaning has the same purpose, but it is typically more cost-effective than solvent cleaning. This cleaning is made primarily of water and is intended to be diluted at the customer site. On average, this cleaner is diluted 5 to 10%. And the formulation has more flexibility, ranging from acidic to neutral to alkaline, giving different cleaning characteristics. This can make formulating a little more daunting given all the ingredients needed for the aqueous cleaner. And here's a quick snapshot of the types of aqueous cleaners that can be used in metal cleaning operations. A mild surfactant or mild alkaline cleaner can be used in various applications, and it's typically used to remove oils, waxes, or greases. And depending on the formulation, ferrous or non-ferrous metals can be used for this cleaner. And then you have high alkaline cleaners, which are similar to mild alkaline, but caution must be in place for the type of substrate used. In this case, high alkaline cleaners can cause corrosion on non-ferrous metals. So this type of cleaner is better left for ferrous metals. The pH of these two cleaners can vary between above neutral to 14. And now moving on to the middle part, the neutral cleaners. These can be used in a variety of applications, but they're typically not as effective at removing oils, waxes, or greases due to their chemistry. And as the name states, the pH of the neutral cleaner is about neutral. So they're safe for various metals, but they can really only remove surface layer soils. And then moving on to the acidic cleaner. So acidic cleaners are typically used to remove metal oxides from the metal piece and are used as a post-machining or post-cleaning or preparation step after most of the soil has already been removed. The metals that can use this type of formulation depend on the acid used, And then finally, there could be a rinse step included as well, which may only consist of water, or it may consist of water with a small amount of surfactant, or it may have a combination of surfactant along with corrosion inhibitors, or it might just strictly be a corrosion inhibitor with water. But the idea is here is to remove any sort of final contamination before the piece goes on to its next step. All right, so we'll go through a couple of slides on the types of surfactant chemistries that you may run into. And so for the remaining of this presentation, I'll focus on aqueous cleaners and the properties related to the surfactants that can go into these aqueous cleaning formulations. All right, so what is a surfactant? So the name comes from its function, which is a surface active agent. It reduces the surface tension of a liquid, allowing it to spread and penetrate the surface. So for the purpose of this presentation, this means it's able to grab dirt or soil off the surface of a substrate, allowing that soil to be removed.
And if I could jump in here, that
Sure.
surface tension modification, that word tension, that's where we hear some people call these tensides.
Yes.
So if you've heard that phrase, that's what they're talking about is surface surfactants or tensides. So
Yeah,
I've heard that a lot of times in European areas, but like
good point. Thanks. Yeah. I'll just out of habit, I'll probably just continue.
Oh yeah, I was just pointing that out in case some
surfactant.
people were, wondering what a tenside was. Yeah.
Yeah. So the way surfactants work is they form a micelle, and I have a picture here of the micelle with some soil dirt. And so a micelle is formed when a group of hydrophobic tails conglomerate together, leaving the hydrophilic end on the outside of the micelle. And so since the oil is hydrophobic, the oil soil becomes trapped within the micelle, and then the hydrophilic head helps carry the micelle away from the solid surface in water. The main types of surfactants are nonionic, anionic, cationic, and amphoteric. For this presentation, I'll focus on the nonionic surfactants. Nonionic surfactants have polar head groups that are typically not electrically charged, or they're not electrically charged, making them excellent for emulsifying oils. And then you have anionic surfactants that have a negative charge on their hydrophilic ends, making them function as a dispersing agent for cleaning formulations. And so in a lot of cases, you can use both the anionic and the non-ionic together to help lift and suspend soil dirt from a surface so that it can be removed. And then cationic surfactants have a positive charge on their hydrophilic end, giving them anti-static characteristics such as fabric softeners. And then amphoteric surfactants simultaneously carry the anionic and the cationic hydrophilic group with acidic and alkaline properties. And these are typically used in personal care formulations as milder surfactants.
That's interesting. Are some of them left behind, like in the fabric?
I'm actually not too sure. We actually do have a personal care group here, so it's something I could probably ask them how that works.
That's just curious. That's neat.
Yeah. Okay, so now we're going to go back to organic chemistry, and if you haven't took organic chemistry, don't worry, I'll make this quick and hopefully painless. So to produce a non-ionic surfactant, you'll need a starting alcohol, ethylene oxide, which I'll refer to as EO, and a catalyst. And to give the surfactant different characteristics, you can also add propylene oxide, and in some cases, I'll probably refer to this as PO. You can also vary the amount of ethylene oxide and propylene oxide added to the starting alcohol backbone to give different surfactant characteristics.
So the R on the starting alcohol just means there's could be a bunch of different stuff, different parts to that molecule. There's no elements.
Yeah, it's referred to the carbon chain or the starting alcohol portion. And then in some other slides, I'll show some actual structures so you can see that.
Yeah, it's a placeholder. Yeah.
Oh yeah, here, like in this image I have here. You can see my cursor, right? Yes.
Yes.
Okay. Yes, this part here is the R group. So with all of the starting alcohols available for a chemist to work with, this combination of 3 items can lead to hundreds of different surfactant combinations. And here I've listed some common terminology that I may speak about during this presentation. So propoxylated means adding propylene oxide. Ethoxylated means only adding ethylene oxide. And then alkoxylated refers to adding both ethylene oxide and propylene oxide.
Mhm.
And as discussed in the earlier part of this presentation, my colleague and I underwent a 1.5 year long project where at the end, we learned different patterns associated with the starting alcohols used, the amount of ethylene oxide, and the ratio between ethylene oxide and propylene oxide, and how that played a role in their performance. And so here we notice some trends with the starting alcohols. So as you increase the chain length of the alcohol, that R group there, you will also increase foaming properties and emulsification properties. As you increase the chain length, the water solubility will decrease. And so the next portion here. So as you increase branching, most of these properties do not change, but as you formulate, you'll notice some difference whenever you're using the linear versus the branched alcohols, starting alcohols. And then as you change to aromatics as a starting alcohol, you may notice more significant changes. So the cloud point will typically increase, oil rejection properties will occur instead of emulsification properties, and then foam will tend to decrease with the aromatic starting alcohols.
Yeah, Stephanie, can you explain a little bit about what cloud point is for those?
Yeah, sure. I'll explain cloud point.
Computing, yeah. It's not where you store your data.
Yeah.
I didn't think of it that way. Yeah. So cloud point, it's usually it's a physical test that you run on the surfactant, or actually not just surfactants. You can do it with other chemistries as well. There's two different ways to do the test method. One is just in water, and one is in a water glycol mixture. And the glycol mixture is to help increase the cloud point. So let's say if the cloud point is below room temperature, you won't see it, or it'd be very hard to test. So you increase the cloud point in a glycol mixture to then give a number. Whenever you are formulating with a surfactant with a certain cloud point, you have to be cautious of, okay, what is the temperature that the application is being run at? So you don't necessarily want the surfactant to fully split out of the solution, or maybe that is something you want to do at the end. So you need to know the cloud point to know when that surfactant is going to exit out of the water solution. So that's essentially what cloud point is.
So it becomes cloudy, I guess, as the surfactant starts to aggregate more and more.
Yeah.
It's less soluble at that temperature. And that's
Yeah.
what scatters light and makes the solution look cloudy. Okay.
And then eventually splits out. Yeah.
Yeah. So it's the beginning of phase separation.
Yes.
Okay,
Yes.
excellent.
So all right, here we have whenever you're, so the previous slide was about the alcohol, the starting alcohol. This one is about what happens whenever you add EO or PO to the starting alcohol and the trends associated with that. So as you can quickly see here, they have opposite effect on the performance of the surfactant. As you add EO to the starting alcohol, the foam profile, hard water dispersion characteristics, HLB, water solubility, and cloud point all increase. And then we explain the cloud point. So the HLB value, what that means, HLB is a hydrophilic lipophilic balance. And this means it's a ratio between the molecular weight of the starting alcohol, which is the lipophilic component, and then the hydrophilic component, which in this case is EO. The values are typically between 0 and 20, and formulators use this HLB value to determine either how to formulate with this surfactant or also what sort of soils they're trying to remove. And then hard water, oh, sorry, go on.
Just real back to the cloud point for a second. In PQCW, we've talked about the KB number, the caributanol number, and that's cloud point test. You want it to be higher because it means that more of a certain kind of soil will dissolve before you get a cloud in whatever you're using, before you get a cloudy mixture.
Yes.
So you
Yeah,
want-
that's
Yeah.
true.
And so
Yeah.
in this case, you could put more surfactant in water with ethylene oxide or with EO than EO. Yeah.
Yeah. So hard water I have listed here as a characteristic. As you add more EO, the hard water dispersion increases. And what hard water dispersion means that the product can disperse hard water soaps within a solution. And hard water soaps can build up in a system, causing nozzles to clog, and that could potentially lead to part defect.
Mhm.
And then
And I had made the comment on this when we were talking about this earlier, that, why not use reverse osmosis water, or DI water?
yeah, and I mean,
you had a good reason. So yeah.
I mean, ideally, DI, RO water is the best water to dilute any sort of product in. But if, someone has maybe a 10,000 gallon system, it doesn't necessarily make sense to use RO, DI. It makes better sense to use city water. So and there's solutions to that you can put in place to help with that problem.
Mhm.
Yeah.
And so adding PO or propylene oxide to the starting alcohol. So all these same physical characteristics with adding EO, they're the complete opposite with PO. And to add more complexity to the situation, as stated before, you can add both EO and PO, which creates a whole new set of molecules giving different characteristics as well. And I'll get into some of those characteristics that we noticed as we're running through this test. All right, so here's the test and results. And just to show you what we were working with, we had various starting alcohols to form the backbone of the surfactant. Some were linear, some were branched, and some were aromatics. We had a variety of chain lengths with the linear and branched alcohols from C6 to C18, and then variations in between. We also had combinations of surfactants that only contain EO, and then some that contain EO and PO combinations. And overall, we tested about 40 different surfactants. And there's a pretty picture, aromatic, right here, and then the R groups.
Mhm.
The aromatic's the little hexagon,
Yeah.
alternating double bonds.
So for the 40 different surfactants that we tested, we performed these tests listed here. We looked to see if the surfactant was water soluble, and then we looked at the cloud point in either a water mixture or a glycol mixture. We also looked at the formulation synergies and acidic and basic conditions and determined if surfactant could be used as a coupling agent. We used the in-house test method for the last 3 tests here: degreasing, emulsification, and foaming. And I'll get into a little bit more details about those testing in the next few slides. So here's the degreasing test procedure. So first we need to develop a dirt soil. And for the soil formulation, we used a combination of 5 things: a water displacing component, an anti-wear hydraulic oil, a cutting and grinding fluid, carbon black, and iron oxide. We then developed a very basic cleaning formulation. And by basic, we picked a formulation that contained only a small amount of the alkaline component and a coupling agent for the water and soluble surfactants. So if you do repeat this procedure, make sure you have a control in place. For us, the control was a formulation without surfactant. And here's some details on the equipment used during this degreasing test. A stainless steel coupon was used to hold the soil and the dirt on the coupon. And then this test was performed on a stir plate in a 150 milliliter beaker. The test was done at room temperature, but you can modify the temperature to suit your application needs. We then had to develop a procedure and make sure it was repeatable, and gave us % soil removal. We cleaned the coupon prior to testing, then the coupon was weighed, the soil was applied evenly, the coupon was baked, and then reweighed to get the actual amount of soil added, and then the cleaning test began. After the cleaning test was complete, the coupon was dried and reweighed. And so here's some images of the actual test and how it looked like. We made sure we had the same size beaker for each test and the same amount of fluid in each beaker to ensure reproducibility. And then the image on the right shows how the coupons looked immediately after the cleaning procedure. And here are results. We did have a control in place, which was a formulation without surfactant, and this did show very poor soil removal, which helped justify our test methods. The bar graph on the top represents the actual results. The blue line across indicates the surfactants that showed a greater than 85% removal, which was considered to be good at degreasing. And the fluid that we tested contained about 5% of the surfactant, and then that was diluted down to 5%. So from these results, we were able to come to some conclusions. Surfactants with poor degreasing properties had starting alcohols that were aromatics, or surfactants that had a higher PO to EO ratio on the alcohol backbone. Surfactants, and then also the third one, surfactants with lower chain length starting alcohol backbone also had poor degreasing properties. Those with good degreasing properties had a higher carbon chain length, and they also had more EO to PO ratio, and these showed good degreasing properties.
We had a question pop up to remind this person what the temperature of the bath was for the cleaning. Was it room
Oh,
temperature?
it was room temperature for the
Okay.
test that I did, so 25 C.
Okay, great.
But yeah, if you know what operating temperature you have, and you can, this is how you should run the test, then definitely go for the actual operating temperature.
Sure.
Okay, so now the foam test procedure. So in this case, we use the CETA foam analyzer, and we did all 40 different surfactants for this testing. So the way this machine works is it feeds the solution through a reservoir into a testing cylinder, and then the cylinder has a blade that produces foam by rotating the liquid at various rotations per minute. And then needles come down onto the solution, detecting how many milliliters of foam have been generated during this test. The temperature can be controlled throughout the testing, and we chose 20 C as the operating temperature for our test, and each surfactant was tested at 0.1%. The solution was rotated 1200 RPMs, 30 times with 10-second intervals. And then we also measured foam decay, and this was measured after the 30th rotation for 10 minutes. Okay, and so here's the results for the 40 surfactants. And to determine how to consider, like if one surfactant would be considered low foaming or high foaming, we looked into surfactants that we produced and how customers would tell us if a surfactant was low foaming. And then we drew a line across to indicate where low foaming and high foaming met. So the low foaming surfactants were typically aromatic starting alcohols with EO only. There were also linear alcohols with EO and PO, and then lower chain length linear starting alcohols. The higher foaming surfactants were linear starting alcohols with EO only. And now keep in mind, this test was only done at one temperature. And this again is where CloudPoint can come into play with foam. So if you can imagine, as you're coming closer to the cloud point of that surfactant, the solution's becoming hazy, and therefore you have foam collapse occurring at that point, especially whenever the solution completely pops out. So as you get closer to the the cloud point of the surfactant, you'll notice that foam will drop very rapidly. So this case, this is only done at 20 C. So if you're going to repeat this test, probably do it at the running temperature, the application temperature.
There was also a question about the branch behaviors. Is there any information on the branch versus linear?
So for a lot of these, they did perform similarly. Where I did notice some differences was with formulating, and my presentation doesn't quite cover that. But if this individual wants to reach out to me, I can talk about in more in depth what I saw with linear versus branched.
Okay, that's great.
So for emulsification or oil rejection test, so we had to design a test where we're introducing some sort of foreign oil into a surfactant mixture and see how the surfactant interacted with the oil. We tested 1% surfactant in DI water, and our foreign oil that we used was a honing oil. So we agitated the mixture and then observed emulsification or oil rejection properties over an hour. So to determine how to read the results, we use the following rules. If the layer below oil rejection was transparent, then it was considered poor emulsification. But good oil rejection. If the layer below the oil rejection was opaque, it was considered excellent emulsification. So this image that I have drawn here shows what we were observing. The black line indicates a piece of paper that I had behind it to see how transparent, translucent the solution was. So if the surfactant had good oil rejection properties, we typically be able to see through the graduated cylinder, and then there would be good oil rejection at the top, like the oil was pretty clear to its original state. If the surfactant had good emulsification, we'd either see no black line or barely be able to see the black line. And there was usually a cream layer at the top as well.
Okay. Are y'all seeing a glitch? My computer monitor is glitching a little bit. Everything good on your end?
I'm okay.
Okay, then let's keep going. I won't touch anything. We'll just go.
So here's the summary of what we noticed. So shorter chain length starting alcohols and aromatics had excellent oil rejection properties. And for emulsification properties, we noticed that carbon chain lengths that were greater than 10 had good emulsification. And if the surfactant had a higher EO content, it also showed good emulsification properties. Keep in mind, this test is specific to this type of oil. So I'd recommend performing this test either in a variety of oils or soils, or if you already know what type of contaminant your cleaner might come in contact with, it'd probably be good to do it that way. So from the previous slides, I described how we ran the test to verify surfactant performance, and then trends as we plotted the results. So for the following slides, we'll show how we took this information and developed an online tool to simplify the surfactant selection process further. And so, as I just stated, we created this online selection tool, and the link will be provided after this presentation. So this tool helps narrow down the surfactant selection process by allowing you to select surfactants based off of their performance, application, physical characteristics, and formulation compatibilities. So for example, if you're looking to make a formulation that provides excellent degreasing, emulsification, and low foaming, you can check all three of those characteristics. And maybe you want to add, like you want this type of surfactant that's good for spray application and soluble in potassium hydroxide, you can check those two as well. And this will help narrow down your selection from originally 38 that we have listed here down to just 6. And so this is an excellent tool for a formulator to develop a cleaning formulation. This can take some of the guesswork out of testing new surfactants by just narrowing down the types of surfactants to test. So feel free to check out this tool, play around with it online, and feedback on this tool is welcome as well. And I've selected some of our top low foaming surfactants to discuss with you quickly. And the reason why I chose low foaming is because I've noticed this is a trend with metal cleaners due to the types of cleaning apparatuses where there's a higher PSI being pushed through the nozzles. The first column I have listed here is Genapol A55, which is excellent oil rejection. It has excellent oil rejection properties. It has excellent solvency characteristics, hard water stability, and has a high cloud point. And I also want to point out the Genapol A55 because it acts as a good coupling agent. And what coupling agent means is, let's say you have a formulation that's tending to split out or cloud out even at room temperature. If you add a surfactant like Genapol A55, this will help bring the solution together. In some cases, not every case, but most cases, it brings the solution back together. So moving on, Genopol EP 2584 is EO and PO containing surfactant that has excellent degreasing properties and is soluble in various cleaning formulations. And then there's Genopol EP 2556, which is also EO PO containing surfactant with a slightly higher cloud point than the 2584. And now Genopol EP 2484 is similar to 2584, but it's from a naturally sourced alcohol. And then last, the Genopol BA 040, it's similar to the A55 that I have listed there. With it has excellent solvency characteristics, a high cloud point. And now beyond just these that I've listed here, we have many other surfactants to choose from, and we also have the capacity to develop new chemistries. And in most cleaning formulations, you can use multiple surfactants to achieve your desired results. And I did a little bit of work with these surfactants and created a couple of guide formulations. So keep in mind, these are starting formulations and just use them as a starting point towards your formulation. So here's two examples that I put together. The one on the left is a formulation that's designed for ferrous and non-ferrous metals. And the one on the right is designed for ferrous metals. So keep in mind, these are example formulations utilizing Clariant's surfactants. Genopol EP 2556 was picked for the multi-metal, and then Genopol EP 2584 was picked for the ferrous cleaner. They both do include the coupler, Genopol A55, but the main difference between these two formulations was the builders that were chosen. So sodium metasilicate and TKPP were chosen to prevent staining on aluminum, where the typical potassium hydroxide was picked and designed for the ferrous metals. I tested both of these for the degreasing test, and both did perform well. And so thank you guys for your attention. I just wanted to highlight again the main takeaway from this presentation. So please challenge surfactant manufacturers like Clariant to design molecules to address your specific pain points. And as you can see from the previous slide, there's hundreds of different combinations to choose from. So and now I guess it's time for questions.
Very good. Thank you so much for that.
So,
Like I said, I'm having some technical difficulties on my end. So Barbara and Ed, I think you'll have to handle the Q&A. I'm reluctant to try to poke on anything.
don't touch it or we'll all go away.
Yeah.
So lots of specific questions, one general, one, yes, the video will be available along with the slide deck in as soon as Darren is able to put it together and it'll be posted. Another question is, are there any studies about the types of surfactant residues remaining on a ferrous surface and their influence on corrosion rates? That's a great question.
Yeah, that's a very, very good question, very specific as well. It's not something I have necessarily done, but you know, that would be a really interesting study, especially I come from a metalworking fluid background, so of course corrosion protection is incredibly important. So you know, reach out to me on that individual question. I'll see what I can do.
Sure.
And a faster test for corrosion rates would be the metal chip test on a filter paper with the material on it. Maybe talk with them about that.
There was another question about concern about residue, and are any of, I think it's related to the corrosion. It said we're concerned about residue, and are any of the surfactants more difficult to rinse?
Yes, that's another good question as well. I didn't do any sort of rinse study on this. I could see where you could easily do this. So, you know, probably, again, I hate to repeat myself, probably reach out to me individually if you'd like. I could imagine a few tests where you could maybe see what the actual residue is left on the metal piece. But I didn't do any of that.
But when it gets into like medical device use and aerospace, they get persnickety about it.
Yeah.
Yeah, we had one question. Please tell us what you mean with water displacing commodity chemical in your soil.
Oh, with my soil
Yes.
that I used. Let's see, I don't want to get specific with name brands. But if you were to Google water displacing commodity chemical, it probably would pop up. It's usually typically to for door hinges to make them less squeaky.
In your garage, probably.
Okay, yeah. Let's see.
The initials W, water displacing gives you a hint.
Yeah.
WD, and
Yeah.
there's more than 39 and less than 41 of them. It's
Yes.
Just not to give you too much of a hint. Yeah, that's a real difficult, that tends to form a lot of residue, that water displacement between 39 and 41.
Yeah.
Yeah, absolutely. Yeah, so I'm really pleased that you're giving people difficult questions to ask their cleaning agent suppliers. That always makes me happy. It's more about what's in the bottle. There's a question somewhere about measuring the foam, other than the fact that the whole room fills full of bubbles. How do you
how do you test
the spray for for foam? Yeah.
So I'm going to probably refer back to my metalworking fluid background. There's a few ways to do this. And what you're just going to have to do is probably figure out what method duplicates the situation the best, which really there's not one true method that will duplicate it other than actually a field trial. So some options besides the CETA that I had done, you could probably do a blender test where you blend it for, let's say, 30 seconds to a minute. And this is shearing. So this is not necessarily pumping air through it as what would happen with a nozzle. You could shear the fluid, pour it into a graduated cylinder, and then measure foam height that way. So that's one way to do it. There's also some other foam analyzers that are on the market today where they actually introduce air into the system, and then they'll I guess the terminology is purging air, and then they will measure the foam decay that way. And it has light scattering and videos and very fancy things going on there. So there's a few ways to do it. I picked the CETA method for this test.
A lot of times we'll use video recording, and you have the timestamp on the video, so you can certainly very accurately measure decay rate in the graduated cylinder with the video.
Yeah.
Let's see, what are we?
It's tedious.
Okay. Let's see. That's an interesting one. There are a lot of interesting questions. Yeah. I anticipate pressures in the marketplace to move to biosourced surfactants, and I'm curious about percentages of surfactant catalog that are biosourced. Yeah, that's a really important trend.
Yeah. I know that we're doing a talk, Clariant, we're doing a talk on that. It's a part that I'm learning a little bit more about, so I don't really want to speak to it and say anything, incorrect. But I know, EO and PO come from the ground, or, mineral-based crude oil. So, is there a trend moving towards naturally sourcing everything? With your starting alcohols, you can do some of that already. The EO and PO portion would be a little bit more difficult.
Sure. Doesn't it get a little into the issue of purification and things like that, because you've got a plant usually, and then yeah, so it hasn't had millions of years to sort of filter, but it's a real interesting, I think it's an important trend.
Yeah.
Which alcohol bases are more available in the market, and consequently which surfactant range is showing more market shortages? In other words, are certain alcohols going to be more readily available and therefore more widely used to make the surfactant?
Oh man, that's a really good question, especially in today's.
Autonomous, not
Yeah.
Yeah.
Hard to know now.
No,
Yeah.
I feel like that's changing almost daily.
sure.
So personally, I'm a formulation chemist. So I don't necessarily deal with that too much, but it's a great question. And if you bring that to my attention, I can ask some of our account managers and people that
Sure.
are they know exactly what's going on right now.
Well, we'll pop those questions back to you.
Yeah.
Yeah, we'll get everybody some answers.
So, yeah, if I think I know what kind of surfactant I need, how do I get some to test?
So for us, it should be pretty simple. The tool that the link will be shared, after this presentation. If you click through that, there's a way to ask for a sample, and then that goes directly to our sampling sourcing center. So that's one way to do it. Another way to do it is you could email me directly, and then I can help you out with that as well.
Okay. And that's going to be mainly used by formulators, right? We're just
Yes, let's make an emphasis on that.
not
Yes.
by, gee, my cleaning isn't quite correct. Can I add a cup full of this?
No.
We're not going to do
Yeah.
it that way.
Yeah, so the person who's putting together that formulation that contains the water, the builder, that would be considered your formulator. They usually sell the actual, finished product to then the end user. So they would be the ones that would sample these surfactants. Yeah.
Yeah, and what I think people who clean metals are maybe coming to realize is there's a lot of steps in producing a fully formulated good aqueous cleaning product that's reliable, which is part of the reason for doing this program. Let's see, what have we not answered? I'm losing. There is one. You've talked primarily about metals, but there are some people that do polymeric materials, plastics, or optics. Do you get involved in that field at all, or does Clariant get involved in that field?
For me, I usually work with the metal side, but that's definitely not to say, I work in a group of people that anywhere from kind of as the Clariant business statement at the beginning, I said we have some consumer care people that I'm in contact with. We have crop solution, we have paints and coatings, additives. So there's somebody that bounce that question to me, and I'll find someone who can help you out.
That would help me, because we run into lots of people that say, I'm cleaning metal, and then you look, oh, there's plastics on it, there's glass.
Right.
Yeah, and especially seal compatibility, because in some cases you're still you're cleaning that piece with the seal still on it. And so you have to keep that in mind as well.
Mm-hmm.
Maybe we should advance to the last slide, which has the contact information.
That would be a really good idea.
Let's see if I can do
The
this.
last slide.
Okay, got it.
It goes up on our screen, so there you go. And that is how you reach everybody. So, and you will get, you can jot it down now, and we will be getting posting the slides.
Well, you will get a copy of these of the presentation and access to the video recording.
Yes.
It may take us about a week, but
depends.
Yes.
How's a couple? What's a coupler?
So it's kind of this, probably there's many terms for that sort of phrase. From metalworking fluid background, it usually acts to bring in a solution together. So you're making this solution and it's splitting out, or it looks very hazy, or it's kind of thick and it's not, or viscous and it's not supposed to be viscous. Adding in a coupler can help then bring that solution that's splitting into one uniform clear solution. So that's what a coupler usually does. It's usually this magic type component that helps bring a solution together.
Can you describe the magic in a little more detail than magic, which I think is great?
Well, so my experience is I'll have I'll be making, some sort of formulation, and it's splitting, and I'll take maybe anywhere from 1% to 2%, maybe even up to 5% of this one additive that's considered a coupler. I add it to it, and within usually a minute, sometimes less than a minute, it's turned that cloudy solution to be clear. So that is what I'm seeing. Yeah.
Is
So I can
soluble.
explain it from entropy.
Okay. Yeah.
Yeah, so every
Yeah.
compound you add increases the entropy of the solution, but sometimes you get, in what we call a Gibbs energy, you get a solution that has two minima, and that maximum in the middle is where they'll start to split. And adding an extra coupler will just drop that entropy, drop the Gibbs energy by increasing the entropy just enough to where now there's no bump in the middle. There's no split. It's spontaneous, mixing at all of those concentrations. So it's just an entropy factor.
Oh, goody. Okay.
I have the graph in my head, but I can't draw it because my pen is.
We should all talk about that again. We're physical chemistry. I have absolutely enjoyed this. Let's see, have we covered close to everything?
I think we have.
I think we pretty much have. I think we've answered all questions. There was one about cleaning aluminum. Anything particularly, a lot of people the non-ferrous thing that causes most heartburn is cleaning aluminum. Any particular surfactants that are fabulous for cleaning in aluminum formulations?
So from my experience, most of the time, it's not necessarily the surfactant that plays a role in aluminum. A lot of times it's the other components in the formulation that can play a role. And maybe not necessarily with cleaning, but you want to prevent that corrosion from occurring.
Yes.
So yeah, in my experience, it's been usually the surfactant it will do its job on the surface, but pay attention to the corrosion inhibitors or your builders that you have in your formulation if you're going to be using it on aluminum.
Okay.
Mhm.
Okay.
Actually, there was one other question.
And we apologize
see.
if we missed one. We're going.
Yeah. We'll go back through all of the questions, and if
Certainly.
we haven't answered them, we will make sure that we do. For the degreasing test, what is considered poor or excellent?
Yeah.
Is it a percentage soil removal, about 90%, or why was this value picked?
Okay, so I picked 85. I did have, so the control in place was the one without surfactant. And I believe it performed, I think it was 60%, somewhere around there. And so then I did a calculation of, what the median and the mean of all those surfactants were. I did also throw in some other controls that weren't listed in that presentation, which were chemicals or cleaners I could buy and then test as well. And that's where I came up with 85 was a good number. And yes, there were some that were borderline to that as well. And so this is something that I can share this information, if you reach out to me and I can talk you through what I did so that, maybe you can make a decision yourself if you maybe want to test another surfactant that maybe was close to that border. So, yeah.
So
Yeah, and I'd like to make a comment too on how to set up a trial like that, like you did. It's not that cleaning at room temperature is what you necessarily will do in the end application, but for a trial, you're trying to make it difficult and you're trying to get a spread in the data.
yes.
So doing the trial at room temperature is valid because you're getting a spread in the data. If this cleaner can clean at room temperature, it's going to be fantastic at 60 C or something like that.
So
Very true.
There's a significant subpopulation based on who I know of the attendees for whom 85% removal doesn't mean diddly or squat in the sense that you need to be up in the 99+% soil removal. How do you get involved at all in that, or would you work with final formulators to perhaps optimize those situations, or how would that work?
Wait, what was the?
Well, basically, so 80 for some people, 85% soil removal is terrific. For a significant number of people here today, from what I see, 85% doesn't mean diddly squat, it's still dirty. You need way above 99%, and then you got to have very, very low residue. Would you be working with the final formulator, or do you ever advise the how does that work?
And for another thing to add to the 85%, I also only had a magnet that was stirring. So essentially it was just
Sure.
soaking.
Sure.
There was no mechanical,
Sure, and no
yeah.
and no temperature. That's true.
no,
Right.
and no
So
temperature.
at heat, if there's a temperature, yeah.
Yeah. So if I were to work with the formulator who maybe had a certain design, or they knew the application, then I would try to help with the application they're working with. For the sake of this test, I tried to keep it reproducible and keep in mind I was testing 40 surfactants.
Sure.
Right,
So
right.
it's not ideal, but it gave me results, and that's what I was looking for.
And I just think that that's worth, pointing out to folks that get hung up on the, room temperature and 85%. That's not your recommendations for the final use.
Good point.
Right.
Yeah.
Those are, again, to
Absolutely
get the
good point.
spread and what are you going to call your good versus bad,
Sure.
It's a
Yeah.
discriminating mark, and that's all it is.
Yeah.
Well, that's great. We've got about 3 minutes left. One more question, Barb, or should we,
Oh, do I have one more
let
question?
them go early? I don't think there'll be
Let
any.
them go early. Let's see.
My students have never complained when I said have a great day.
We were going back and forth through the questions. I think there was a comment way up at the top.
Okay.
Which was this is interesting, and it's a little away from metal cleaning, but bluing agents and fabric softeners and detergents can have non-ionic surfactant like tails, which can be designed to leave just enough color behind to function, and then removed and redeposited to get the proper balance. So what the questioner is talking about is actually, in a way, a beneficial contamination, in a sense that you want to leave a little something behind.
Oh,
And
okay.
I think the applicability to metals is that an RP is a beneficial contaminant.
Yeah.
Yes.
right.
Yeah,
Yes.
yeah,
Yeah. And that's why I was trying to discuss on the rinse step, where, really the rinse step is up to the, where's that part going? What is that part? What do they need out of that part? Which could just be water, or it could
Sure.
be water surfactant, water corrosion inhibitor. So yeah, there's no one straightforward answer. Yeah. And it sounds
no,
like,
and I didn't think
yeah.
there was, and I really appreciate your repeatedly saying to the end users, put pressure on the formulators, bother them,
Mhm. Yeah,
demand more.
Yeah.
I think that's the important thing, which means tell them what you need.
that's
Yes.
right.
Yeah.
Even if you can't use the terminology, go say, this isn't working. What does this work? So what does this mean when it doesn't
Yes.
work? And
And
that's
here's
why-
what I need: no foam or this or that,
yeah,
or we have to use tap
bubble.
water. So what am I going to do?
Yeah,
Yes.
yeah. Okay.
That's great. Stephanie, I really thank you. This was a
I
fantastic
think that was
presentation.
fabulous. I really enjoyed that.
Thank you,
And-
guys. And thanks for
Yeah,
all the
to-
questions. Those are really good
Sure.
questions.
I like
And
that.
to everybody that attended, I hope you learned something. And it seems like you were very engaged with all of the questions. And
Yeah,
so
I enjoyed it.
Yeah.
For the PQCW team and for Stephanie, we'll say bye. Y'all have a great rest of your day.
Bye.
See you next
Bye.
time. Bye-bye.
Thank you for watching this recording of a PQCW webinar. You can find other webinar recordings on our YouTube channel. Like this video and subscribe to our channel, and hit the notification bell so that you'll be notified when we upload other content. Thanks, and have a nice day.